Okay, hello and welcome to my channel. Today we're gonna continue to take a look at the step potential, and this time it would be the third case, which is when your E is less than V naught. And here we will see the quantum tunneling, the actual quantum tunneling. Right, so a quick fix for the last two video, I wrote that k is equal to 2me over h bar e over h bar squared. It was actually supposed to be k squared, and I didn't realize it in both videos, so sorry. So it would be fixed today, so don't worry. So back to our video today. When you have your E to be less than your V naught, well, classically, it would just hit the wall, then bounce back. But this time, it's not gonna be like that. And it's gonna have something that leak through it. And that would be quantum tunneling. Okay, so in this system, for x less than 0, your solution would stay the same with, okay, quick note here again, for your psi on this side, that is aeikx plus bei minus ikx. Maybe this part is needed. Over there, it is ik tilde x. Okay, so we'll take a look at both region here. For x less than 0 and x greater than 0. So for x less than 0, your solution will stay the same. So same solution with k squared this time equal to 2me over h bar squared, right? But what interesting is the next region where x is greater than 0. This time we would want to change it to some kind of decay since our energy is less than V naught, so it would get pushed down. And I think I mistakenly say that they are tunneling when I talked about the scattering state, so that is one mistake again. So sorry for that. Okay, so we would want it to be some kind of decay, so we would take our k tilde to be I kappa. So when you take this, now your kappa square would be 2m h bar square. This is V naught minus E. And your C of ik tilde x now is gonna turn into C E minus kappa x. So that would be the change in our system when you take E less than V naught. Okay, so now let's take a look at our coefficients. And since this part is the decay, it's not really that important. So we will take a look at our reflection coefficient first, which is, well, B over A. B over A, that would be IK. Okay, so be K minus, okay, I should write K and kappa in a clearer way, so hope you guys can tell the difference. K minus I kappa over I K plus I kappa. Alright, so this, you can sub it out. That would give you a minus outside, and inside this turn into kappa, and that one would turn into ik. So now you get kappa plus ik and kappa minus ik. Doesn't look that clear. K, that is K. Okay, maybe I should, oh my gosh. My handwriting is a bit sloppy, so sorry for that. K, this is a K as well. This is a K, this is a K. All right. So what you get ultimately is minus E2i. We take a delta of E, that would be our phase shift. And this, when you plot it on the kappa and K plane, that would look something like this. There we go. So this is the kappa, this is the K. Would be some sort of line. This is to K and I kappa. I kappa, this is K, goes to here. This angle we call delta. Right. So you can sort of visualize that already. This will let you calculate the tangent. Or in this case, we would take the tan minus 1 of K kappa, K over kappa. And some people, usually they would take that kappa over K. So the change here would be that when they plot function of delta and E, that would look inverted. So when you plot the graph of delta E and E, when you do this, the bound here would be V naught, and the bound here would be pi over 2. So just connect these, and it would look like some sort of sigmoid function. So it goes like that. And if you take the kappa over K, the tangent of kappa over K path, it would look something like this. And this cross point would be V naught over 2. Over here it is pi over 4. But today we're going to take a look at the tangent minus 1k over kappa. Expand this, you get tan minus 1 the root of E over V naught minus E. And if you take the other path, this would be inverted. So it would be the tangent of V naught minus E over E and the root. Okay, sorry for that. Okay, so next we're gonna assume our current in the classically forbidden region be 0. So somewhere. Take JC to equal to 0. So now the only part left here in your system is the left part. So now you can get that the current A would equal to current B, meaning that absolute A square would equal to absolute B square. Meaning that these two gonna be the same in amplitude, but they're gonna be different in the phase. Meaning there would be some sort of phase here on either A or B. So I will instead of writing that, I would just write in Word. So a different in the face. All right. Now we're gonna go back and take a look at our wave function. So let's get the easy one out of the way first. When x is in the classically forbidden zone, it would just be ce to the I kappa x. Right now, we're gonna take a look at the left side. Our wave function now is, you would get it from here. So that is your face. Okay. So your wave function now is e minus, okay, from here you can somewhere to write that. Basically from here you can get that b is equal to minus a. So I don't think I need to write that, but I want to, but I'm out of place. So that would be your wave function in the classically allowed zone. And you see that is an exponential minus an exponential. That would yield you a sign. Here's a difference, so that would be proportional to a sine of kx minus delta of e. And to be more precise, that would be 2ai sine kx minus delta of e. Right, so, okay, I forgot the face. The face is times 2i delta. Okay. Yeah, that looks about right. The I sine part, the face, and the coefficient. Alright, that is correct. Okay, and assume that thing in the classically forbidden zone is not important. You can get that our probability density on the left side is for sine squared of the thing inside. Oh yeah, there you go. That would be your probability density. So now you can get that your density is gonna look something like this. Until this point, x equals 0, it's gonna decay. That would be the picture for your probability density. Right, so now we're gonna take a look at the last thing, which is the time delay. And we're gonna make use of our phase shift here. So erase this part. It's gonna be brief. I hope so. So for the time delay, we're gonna take a look at the derivative of our delta of e. That would give us 1/2 1 over e times v naught minus e. That would be your derivative. And what this tells you is that when at 0, it's gonna go, the e is gonna go to infinity. So meaning that the time delay is very large, so a ton of delay. And at v naught, the time delay is also very large. So that would explain a phenomenon where your wave function, when it hit this sort of step or a barrier, it's gonna be lingering a bit before it goes away. So that would explain that phenomena. This is gonna explain later the Wigner time delay. So from here you can find the minimum time delay where the wave function would be just immediately bounce back, and you can do all sorts of stuff with that. So this is another very useful definition or formula. Okay, so that's it for today, and goodbye.